Hi, for the lecture today we are going to talk about the related rates. Okay, where does this topic come from? Well, either in mathematics or in engineering or in physics, you are studying several quantities that are related to each other. Related means if one of them changes, then the other ones will change. All the problems that you're going to face in this section, some problem is explained and rate of change of one quantity is given and you're asked to find rate of change of other quantities. Very simple problems either relate to Pythagorean theorem. If they're coming from geometry, most likely they have something to do with this. In the Pythagorean theorem, which you use for measuring distances and such, you have three quantities. There are these two legs, and then there is the hypotenuse. They are related by this famous quantity, c squared, famous relation, c squared is equal to a squared plus b squared. Now, if you change a, perhaps holding b fixed, and c will change. Or if you change both a and b, c will change. If you want to find out how are their rates related to each other, you have to differentiate this whole equation with respect to time. So you say differentiate with respect to, it's high, right, with respect to time. You need to remember chain rule to do this thing properly. Let me remind you, if you have, say, u to power of n, you want to differentiate that. Say n u to power of n minus 1, then there is a big item here, the derivative of the base is included. So if I want to differentiate this, 2 comes up front, the exponent instead of 2 will be lowered to 1, and then we have c prime, or if you want to write it more explicitly, dc dt. You can either write c prime or dc dt, so long as you remember what the prime means. On right hand side, same story. I'll have 2a, 2 minus 1 is just 1, dA dt, and then other 2b to power of 2 minus 1 dB dt. I can just go ahead and cancel these 2's. They're always there. You can cancel them. Instead of 2 minus 1, just write 1, and then you'll have this nice relation, c prime is equal to a prime plus b prime. Again, the prime here means rate of change with respect to time. So if you have some contraption here and a and b and c are changing in some manner, 2 of them might change. You might specify the changes in 2 of them, and the third one is going to follow from this relationship. And you can find that third quantity by substituting all the other items that you have here and figure out the missing one. Other geometrical problems might be related to circles, areas, and such, and they have a similar flavor. Problems that come from science and engineering, they start by law of physics. Perhaps you have taken a course in physics, you know about the law of ideal gases. Let me explain. Suppose you have a piston. Here's a piston, and there is some gas molecules here. Well, how would you describe this gas here? That gas has a pressure, it has a volume, it has a temperature, and it has some amount of mass or quantity. You might show it by say N. Okay, so we have pressure, volume, temperature, and the amount. Well, these quantities are not independent of each other. Ideal gas law, they say, says that these are related to each other. Simple relationship that connects them says that, for example, P times V is equal to some constant, typically they refer to it by R, this is a constant, times N times T. Never mind where this relationship comes from, it's just something rather reasonable that connects these quantities to each other. Our point is that if you go ahead and change several of these items, leave one of them out, then that one is going to follow suit based on the changes in the other ones. Let me explain this thing in this manner. Suppose you keep this piston here in this place fixed. Suppose that you don't let any gas to go in and out, so the amount is also fixed. So we said fix the volume, fix the amount. Now start heating up the chamber. Let the temperature go up. Stands to reason that pressure inside the chamber is going to go up. These molecules are going to move around faster, are going to bang against these walls faster, and the pressure is going to build up. That's what this thing is saying. If you increase the temperature, pressure goes up, assuming that everybody else is held constant. What we have in mind is that perhaps somebody will come and describe to us how fast is one of these temperatures, the temperature is changing. Say somebody once comes along and says the temperature is increasing at the rate of 10 Fahrenheit degrees per second, a very quick heating up. In that setup, perhaps you want to know how fast is the pressure increasing. Since pressure is related to temperature, in temperature we know how fast that one is increasing, no problem. We can figure out how fast the pressure is going to increase. How do we do this magic? Well, we use related rates. We differentiate this equation. When you differentiate, rates of change is going to come in. You plug in the amounts that you know for the quantities and for the rates of change, and then you figure out the rate of change of the missing quantity. Okay. The best way to learn this topic is just go ahead and solve several problems. Let me go ahead and start by one rather simple problem that's going to take a while, but actually it's simple. So here's a problem. Similar to the problems you see in the text. Suppose a particle is traveling on a curve given by y is equal to, say, radical x squared plus 2x plus 17. At the moment when it reaches x equals to, say, 2, its x coordinate increases at the rate of say 4 meters per second. Question: how fast is its y coordinate changing. Question number 2. Let's make something else too while we are here. How fast is its distance from, say, point 1, point 1 and 3 changing? These are related to that same moment. Okay, let's go ahead and describe the physics of the situation. It's not so important to do a very careful graphing of this curve. That's not really relevant to the answer, but it's good if you want to remember your mathematics to go back and practice some of these things. Just remember how to draw curves and remember the names and such. I go ahead and draw it quickly here and let you think about it. Maybe you want to pause this thing for a moment and draw the curve for yourself. Try to remember what was the name of it, so on and so forth. Okay, here's a curve. It's a hyperbola. Comes down here, turns up, and goes. The particle we are interested in sitting somewhere here, perhaps when x is equal to 2. Let's see, when x is equal to 2, what is y? I put x in my formula. 2 squared plus 2 times 2 plus 17, that makes 25, square root of which is just 5. So this is the point with coordinates 2 and 5. Okay, this blue spot is traveling on this this red spot is traveling on this blue curve. How is it going? Well, we don't know the whole detail of it, but we just know that at this point it's traveling with a specific velocity. Its speed in the x direction is 4 meters per second. What does that mean? Well, when you're traveling on the curve, so your velocity really looks like tangent line to this curve. It's going, imagine this, say a car going uphill. Its velocity is a vector tangent to the curve and going that direction. This velocity has 2 components, one in the x direction and one in the y direction. So by talking about rate of change of x coordinate, we are really talking about this thing. This thing is really dx dt. Dx dt is equal to 4. When you say x coordinate increases at the rate of 4 meters per second, this rate talks about dx dt. Increasing tells us this is positive and the value is just 4. So I know this dx dt is 4. What is it that I'm after? First question is how fast is its y coordinate changing, meaning the rate at which we are going up. This is the rate at which we are going to the right. This is the rate at which we are going up. That is what we are after. Let me write it in some other color. This is dy dt. That's what we want. Or perhaps we want the whole velocity here. Maybe you want this vector, or how fast it is actually moving. Depending on the case, you might solve for any of them. Let's go and get this one, which is straightforward. We want to figure out dy dt. What's our clue? Our clue is that y is related to x by this. So rate of change of y is related to rate of change of x. How do we do this? By rules of differentiation, particularly the chain rule. We are going to go ahead and do that. So let's go ahead and differentiate. So to differentiate, I first write this relationship using the power law, which is easier to work with. X squared plus 2x plus 17 to power of 1/2. How to differentiate? Well, we are going to write dy dt. To differentiate right hand side, let me remind you again, we have this power rule. This kind of differentiation we are going to do, and we are not going to forget this element coming from the chain rule. So let's go ahead and do power up front of 1/2, then x squared plus 2x plus 17 to power of, instead of 1/2, we have to lower it one notch, 1/2 minus 1. Then I have to differentiate this. Let's find the prime of that. To make it clear, let's write d dt of x squared plus 2x plus 17. So our prime here is prime with respect to time. One more round. This is 1/2, that is x squared plus 2x plus 17 to power of, this is minus 1/2. Derivative of this, derivative of x squared with respect to t. I remind you again, we are differentiating with respect to t, and like derivative of a squared was a prime and or a times dA dt. Here thing, derivative of x squared with respect to t has two components. Derivative of x squared itself is 2x, but you also need to multiply by x prime, which is dx dt. Let me write it here. Derivative of 2x with respect to x would have been just 2, but with respect to t is 2 dx dt. So what did I do? I just differentiated this whole thing with respect to x, and since my differentiation was with respect to t, I multiplied by dx dt. Go ahead and double check to make sure that you understood this differentiation. Now let's go to the next step. I write dy dt. Might as well go ahead and cancel this 2 with the 2's here, both of them. So I get, from this parentheses, I get x plus 1. This one to the power of minus 1/2 is going to be same as the item in a radical in the denominator. That's x squared plus 2x plus 17. And now we have dx dt. Okay, so our first job was to differentiate. Now we are actually done. Remember, the location of the object is the point with coordinate 2, and y will turn out to be 5. dx dt was given to be 4. We just go ahead and plug everything here. I want to figure out dy dt. Instead of x, I put my given x, this 2 plus 1. Denominator, you might remember we have done this thing once already, but if you wish to repeat, 2 squared plus 2 times 2 plus 17, that's just the y. dx dt, that's the speed that's given to us, that is 4. So 2 plus 1 makes 3, denominator is 5 times 4. dy dt turned out to be 12/5. So the particle, or if you wish to write 2.4, in mathematics we prefer nice fractions as opposed to decimal numbers. 12/5, that's the speed of the object. In engineering you almost never do that, you just write 2.4, but in math we have our own habits. We try to stick to fractions, radicals instead of decimal numbers. Okay, how about the second question? Second question is talking about perhaps some observer or somebody is sitting at the location 1 and 3. It's a cop standing there watching this vehicle going up. They are separated by some distance. Here is a distance that separates these two. Let's call distance L. How fast is its distance from 1, 3 changing? That is, this L is going to change as this particle goes on the blue line. This green line is going to get longer. Question is, how fast is it going to grow? If you want to track any particle, a car or a satellite, whatever it is, you need to know about these things. So how do we go about doing this? Well, we have to relate this quantity we are after, L, to other quantities we know. What is it that we know? We know the location of this particle. We know it is sitting at, let me draw a second picture, less crowded hopefully. Here was our point with coordinates 1, 3. Somebody is here, is traveling on the blue line. Its coordinate could be x and y, where you remember y was given as radical x squared plus 2x plus 17. These are separated by this. How do you connect L to the location of the particle? That's very simple. That's the Pythagorean theorem. You use the distance formula. What's the distance formula in this case? L squared, the distance, hypotenuse squared, is equal to this leg squared plus that leg squared. Well, what is this leg? You have gone from x equal to 1 to x being just x. So x minus 1 is your run. X minus 1 squared. Plus, what's your rise? You have gone from 3 to y. So you write y minus 3 squared. So we are halfway already. We discovered the relationship between the quantity and some other quantities we know. Now we want to know the rate of change of this quantity. So I have to go and differentiate this. Derivative of L squared with respect to time is going to be 2L dL dt. Derivative of this, 2 up front, x minus 1, 2 is lower to 1. Derivative of the base, derivative of x is dx dt. Derivative of 1 is 0, so I don't need to write. Plus 2, again, the base, y minus 3. Derivative of this is just dy dt. All that is left to do is to plug in the numbers and get what we want. Now let's first go ahead, just for simplification, divide just by 2. So that's all gone. What do we know? At the moment of interest, now we come and say that at the moment of the interest, this particle was at the location 2 and 5. Remember, x was given to be 2. We plugged in, found out y is 5. So that is the moment coordinates at the moment of interest. Now it just comes in. what is the L at the moment of interest? Well, let's just apply it here. In this formula, we have L squared is equal to x is 2 minus 1 squared plus y minus 3, y at the moment of interest is 5 minus 3 squared. So this is 2 minus 1, just 1. 5 minus 3, 2 squared makes 4. So L squared is 5. That tells me L is equal to square root of 5. So this was some side calculation we did here. Let me keep it separate. So this is 5. Excuse me, square root of 5. Just found here. dl dt is quantity we are after. X minus 1 at that moment is just 1. dx dt is the speed that was given to us, that was 4, plus y minus 3, y is 5 minus 3, that becomes 2. dy dt is the quantity we just found, 12/5. So that becomes 4 plus 24/5, and that makes it take a common fraction, 44/5. Common denominator, that becomes the speed. So what we found, now find an answer here. dl dt, I divide by square root of 5, get 44, 5 radical 5. I should not box this thing because really there wasn't anything important about it. Let me see if I know how to erase it. Okay, yeah. We are done. It was a bit long, but we learned lots of things. Hopefully all motion problems we can do that. This is just one example of such problems. Let's go ahead and see if you have time for another problem similar to the items we have in the text. Here, let's see. How about this? Suppose let me write it down. A kite say 50 feet above the ground moves horizontally at a speed of say 7 feet per second. At what rate is the angle between the string and the horizontal? Decreasing 150 feet of string have been let out. Okay, like anything else I do in these lectures, I like you to pause, try to figure out the problem for yourself as much as you can, at least get the picture drawn, get some variable named, write down the rate of change, discover some relationships, perhaps try to differentiate it and see how far you can go by yourself. If you get stuck, then you come back here and then you'll appreciate the steps much better than just by following the video right away. First thing to do is to draw a picture. Go ahead and draw a picture and name the quantities. Which way is the kite moving? Is it moving in your picture? Is it going to be moving right or left? What is it that makes sense? Okay, so once again, pause for a moment, see what you can do, and then come back in. I continue now. Let's draw a coordinate axis. So here is our student John Doe or Jane Doe or somebody standing here trying to prepare for a calculus test, but flying kite is a lot more attractive thing to do. So let's suppose the kite, here's a kite string going out here. Here's our kite. Make the kite to be just this dot. The problem is talking about the angle decreasing. Also, when you let this thing out, the direction of traveling has to be, I have drawn my picture. The kite is traveling this way. Notice it's telling us the kite is traveling horizontally. It's going to be traveling this way. As it goes this way, the string will be stretched out and the angle which was say at the beginning was this big angle is decreasing to this smaller angle. So with these clues I draw this picture. Now I'm going to put some names and numbers here. I have my x coordinate, the x coordinate of this kite, whatever you wish to call it. Then I have its altitude, that's going to be the y coordinate. Then I have the length of this kite, let's call it say L. Using D is not going to be nice because you are going to use D for differentiation, so call distances by L or S or something, don't use D. What are we told? We are told that the kite is traveling at the speed of 7 feet per second. So here is one clue. Dx dt is 7 feet per second. There is no dy dt because we are told this is moving horizontally. What else are we told? At the moment of interest, remember in all of these problems lots of things are changing, and we always bring the problem back to a certain moment, and at that moment we ask various questions. At the moment of interest, this L turns out to be 100 and a string has been let out by 150 feet. This was feet per second. What is the quantity we are after? At what rate is the angle? So we need to call somebody our angle. Let's call it angle theta. So I have to connect this required quantity, theta, to the other quantities about which I know something. I have this x, y, l. I want to connect the theta to these. That's the first step. That gets us the relationship. Then I take a derivative of that, and then I get my related rates. Well, how do you connect this angle to these quantities? Well, that's the issue from trigonometry. You have many ways of connecting this angle to these quantities. You in fact have 6 different trig functions you can use. Any of them would do. None of them will get you to a wrong answer, but some of them are a little bit better than others. What is better? So long as we use something that is a constant, our life is going to be perhaps a little bit easier. So I'm going to use this relationship. I start by saying, let me see, before I go any further, what is the, can you remember, what is the trigonometric relationship that connects this angle theta to y and x? I hope you have taken your trig classes. So tangent of theta is equal to y over x. Okay, by now we are almost 50% done. We have a picture, we have a relationship that we are going to work on. Next thing, we have to know how to differentiate this. To make some room. Excuse me. Okay, we are here. How do you differentiate? Well, what's the derivative of tangent? Derivative of tangent is secant square. But we are not differentiating with respect to theta. It's something we need to keep reminding ourselves all the time. Differentiating with respect to time. We want to know how fast is the angle changing with respect to time. So I'm going to write this by using the chain rule. Differentiate this times the derivative of this quantity with respect to time. How about the right hand side? Who is the changing quantity here? Let's not forget, we said y is fixed. The elevation of the kite is fixed. So y is not changing, x is changing. So we have to differentiate this thing with respect to x. You have to apply either the quotient rule, or here is a little bit faster. So this is y times x to the power of minus 1. I want to differentiate this. Y is constant. Y, derivative of x to the power of minus 1 by the power rule. Exponent comes in front. Exponent is reduced 1 notch, so instead of minus 1 it goes down 1 more notch. And then by the chain rule I have dx dt. Let's clean this up. It's good to write minus up front. It's minus y x to the power of minus 2. I write it here, dx dt. Now to make this formula easier to digest later on, let's remember who is secant of theta. Secant of theta is a ratio of what was it? Ratio of hypotenuse to adjacent. So instead of secant of theta, I'm going to write hypotenuse to adjacent. Since I was squaring squaring secant, I'm squaring each of these. This is d theta dt. Right hand side is minus y over x squared dx dt. Now we are about 95% done. Let's just go ahead. This x squared is same on both sides. You can just cancel it. Bring the L squared to the other side. I'll have d theta dt is equal to minus y over, L squared times dx dt. Here's our holy grail. If you understand what went on here, you have made quite a bit of advance in your mathematics. 99% done. The only thing left to do is just plug in the numbers that we were given. Let's see, what were we given? We were given that the kite is 50 feet above the ground. That is 50. Then L was given to be 150. Dx dt was 7. So let's see if we remember all these numbers as we go down here. So here d theta dt, I forgot already. Y was, okay, it was 50 feet above the ground. L was 150 L squared. Dx dt, that was we said 7 feet per second. So what is this? Minus 350. Maybe I should not have multiplied. Let's just minus 50, excuse me, times 7. Let's write 150 and 150, simplify before we multiply. So I have this one, I can simplify by a factor of 50, get 3 here, minus 7 over 450. What is the unit of this? Let me pause for a moment and you can you figure out what's the unit of this? The rate of change of an angle with respect to time. How is this angle measured? Remember, all the formulas in calculus, angles are measured in radians. Now we are taking rate of change with respect to time, so this is radians per second. That finishes up the job for us in this problem. Okay, let me say a few words here. Perhaps you might be a bit overwhelmed by the problems we are doing. They are substantially different from the problems in the previous section where you had to just differentiate a function where the formula for the differentiation was given. The problem we are doing right now draws on your knowledge from a variety of sections. So basic science, ideas about motion and such, differentiation. There are so many variables, it looks like an alphabet soup, and all of that. Essentially in calculus there are 3 sections that are very challenging, difficult for the students. One is the section on graphing, producing a correct graph and analyzing it. The other one is the section on related rates, the problem we are going to be facing in this section, and the problem related to optimization that's going to come up pretty soon. And these are 3 peaks in calculus. You measure your knowledge of calculus by figuring out how many of these problems you can actually do. It's just one level higher than everything else. So make sure you do the very basic problems in these sections, the beginning problems, and these other ones do the best you can. Let me go ahead and perhaps add one more problem here, a bit easier than the one we did. Here, let's say we are going to have 2 cars, and they are going to be traveling in 2 streets at an intersection, and we want to see how their distance is changing in time. Car A starts 10 miles west of an intersection and travels east at, say, 20 miles per hour. Another car B, starts, say, 30 miles north of of the same intersection, of course, and travels north at let's make another number, so 40 miles per hour. Question A. How far apart are they 2 hours later? Hours. Question B. Well, one is traveling west east, another one south north, and they are gonna move away from each other from the numbers, it looks like. Question is, at what speed are they gonna move away from each other? Well, let's draw a picture again. My recommendation, draw a picture, try to get something going on. Naming of the quantities, their beginning values, their rate of change, their relationship with each other. Go ahead and differentiate, and then come back and see if you were on the right track. Let's see. Start by drawing our intersection. Whenever you feel you had enough clues to stop this thing, do it yourself. Here is let me see, when I stand toward north, this gotta be east, is that right? This is west, and hopefully this is still south. Our car A, starting to the west of the intersection, and then it's traveling this way. So this is 10 miles to west, so it's 10 miles west will be -10. It's going at 20 miles per hour. 30 miles north, perhaps it's so this is car A, car B, 30 miles north, so this is 30. That is traveling a lot faster. That is traveling 40 miles per hour. Okay, is that enough clue for you to get going? What are we going to do next? Well, we have to figure out circumstances 2 hours later. Where is this guy going to be 2 hours later? Well, in 2 hours, this is going to travel 40 miles, starting at -10. Where is he going to be on the other side? 40 miles. To the east of this, that's going to be location 30. Now I'm a bit of a trouble here because this other one 2 hours later going at the speed of 40 is gonna be traveling an extra 80 miles. He is at the location 30 now, and so he is gonna be at 110. Is that right? So we are up here perhaps. Maybe I throw another color. So how far apart are they 2 hours later? This is I'll cheat a little bit. Suppose this is 30. This is the distance we are talking about in part A. What is L? Oh, well, that is easy to answer now. L is square root of 30 squared plus 110 squared. What is that? We go ahead and figure it out. 30 squared, that is 900. 110. 12 squared is 121. So that is square root of 13,000. I didn't adjust it to be a whole number, nice number, but well, that's the distance. That's how far apart they are at 2 hours later. So you can, if you're curious about the distance, now you use your calculator and figure out what that is. So it turns out to be approximately, say, 114 miles, point, say 02, etc. Now, part B is more interesting. It's more calculus there. You have two ways of answering this. Remember, part car A is traveling. It has its own coordinates. Let's call it X. And we have the other car B, has its own coordinate, that's Y. So what's the relationship between L, X, and Y? Very simple. L squared is X squared plus Y squared. Now you remember our discussion at the beginning. In the beginning, we had, you go ahead and differentiate this. You can drop the 2's, and you're going to get L dL dt is equal to X dx dt plus Y dy dt. So what is L? L is this. Once again, in mathematics, you keep the numbers as they are. Try not to go to that unless it really bothers you. So dL dt. X at the moment of interest is 30. Dx dt. Who's dx dt? Dx dt is the speed of car A, that's 20. Y was 110. Speed of this other car was 40. So the LDT, the rate at which they depart from each other at that particular moment, is going to be 30 times 20, that is 600, and these two is 4,400. Now I divide by square root of 13,000. This is going to be even 5,000 over 13,000. You divide that, you get, let's see, what do we get? You use your calculator and find out that this net separation speed turns out to be 43 85. The unit is miles per hour. So these two cars are going to be moving away from each other at that moment, 2 hours after they started, at the rate of 43.85 miles per hour. Okay, I guess we had enough for today, and from this section, go ahead and do all the problems of this section, perhaps a few extra ones. If you have questions, let me know. Good luck and God bless.